Good, so welcome back to CSOC TV. Now, we've heard a lot in the last couple of years about big data analysis and Internet of Things, particularly at CES, the Consumer Electronics Show, and the same affiliated with the ICCE conference where we are right now. Now, there's another term being used, and that is cognitive IoT. And with me to explain what that is Martin Kienzle from IBM Research. Martin, thank you for a very interesting keynote just now on day 2 of ICC in Las Vegas. Would you be kind enough to explain to us what you mean when you talk about cognitive systems and cognitive IoT?
Cognitive systems, the most important part is understanding the data. That is, you go beyond the pure statistical level actually to a semantic understanding of data. And so what we're saying is a shorthand for defining what cognitive systems are is URL. Understand, reason, and learn. So reasoning in the semantic level and also learning, that is self-learning systems, those are all aspects of cognitive systems.
Could you give us an example of a self-learning system, either one that exists or one that might exist in the future?
Self-learning systems, for instance, one of them I talked a little bit about is actually Chef Watson. That is, it proposes recipes, and then when people use them, they say, I don't like it, or I do like it, and then it updates its knowledge about what people like. Another self-learning system actually was the Jeopardy system that we used to win the game show some time ago, because we simply told the system this answer was wrong, that would have been the correct answer, and then the system had to go back itself to figure out how would it have to change itself to come to the correct answer. And as you saw, it took actually a long time for the system to find out how it needs to align the algorithms to get the right answer. But that actually was a self-learning system. And a lot of the technology that is based on this today is also self-learning.
Okay, good. So if I understand correctly, in the way that self-learning systems go beyond, or cognitive self-learning systems go beyond some of the recommendation systems that consumers have become familiar with over the last few years, such as the Netflix film recommender or Amazon recommending certain purchases, we're seeing this arising in more and more areas of our lives. But the self-learning systems that you're talking about are a kind of level above this because they understand semantics, context, and they have a greater understanding. They're working on more dimensions. Is that right?
That is exactly correct. That is, a lot of the typical recommendation systems, they simply talk about statistical clusters. That is, you could actually say they throw the data into the Cuisinart of statistics and look at what comes out. But what we're trying to do is saying what it actually means. And so one of the other examples are in that system that I showed, where we look at people's activities of daily living. So again, the question is, how can we determine whether somebody takes care of their nutritional needs? So it's not looking at how often they open the refrigerator. What does it really mean? Is somebody taking care of their nutrition? And by the way, those are also self-learning systems. That is, simply by recording what people did, then we found the clusters of behavior, and then from there we could actually detect what is the semantic meaning of those clusters. And raising it to the semantic meaning is actually what we believe makes a system to be cognitive.
Okay, so you talked a little bit about k-means as a clustering algorithm.
That was one of them.
Why would you expect that, or why do you think you found that was one of the better performing ones?
It was simply experience. I mean, to tell you the truth, I'm not really the deep statistical analytics kind of guy. That is, in this one, I simply report about a project that some of my colleagues did. But what you saw on the table was, we didn't know which one was the best algorithms, and the reason they picked k-means, and maybe it was a little bit difficult to see, it had the lowest rate of false positives and the lowest rate of false negatives, and so in that sense, this is what science is all about. You make a hypothesis, you try it out, and then you determine did it work or didn't it.
So if I remember correctly, that was about 6% false positive and
Yeah.
true negative. So is that good enough for people to use in homes?
In some cases, it probably is. But as I also said, when you act, you have to be very defensive. You have to be extremely cautious and always sort of operate at a fail-safe level. And in most cases today, my personal opinion is that I would probably not be ready to let a system act yet. But I do think eventually we will get there, just as we are getting there, for instance, with self-driving cars. And as you see in the news, they are allowing self-driving cars on the road. Some cars are being certified. And so while personally I still feel a little bit queasy about it, I think over time it will come.
Okay. So would you be willing or daring enough to hazard a time frame for when we might see such systems in our homes?
At the beginning systems, that is things that, let's say, maybe determining whether an alarm, say security alarm, is correct or not, that could be actually within 2 or 3 years. I think that is really quite, those are things quite simple. And also, if you ask a human to act, then there is always a safety valve. And so those kinds of systems, I think, could come pretty quickly, whereas autonomous actions, depending on the application, maybe a little bit longer, maybe 4 or 5 years out.
Very interesting. You just used the word application. Now, working with algorithms, one sometimes finds that an algorithm, one has to tune an algorithm to work for a particular application, and there's plenty of discussion of whether it's possible to make magic algorithms that are cross-domain, or whether each algorithm or system containing algorithms is really just a bag of tricks that's used for a particular use case. With regard to you mentioned the Watson that was used for Jeopardy.
Yep.
What do you see in terms of challenges in using that in other domains?
One of the biggest questions is knowledge acquisition. But one of the things that we actually showed this time at CES was if you have a reasonably well-defined scope in which you want to reason, then the knowledge acquisition can actually be really quite simple. So we actually had their consultant about weather, and you could ask it, do I need an umbrella today? And so the system knew that we were in Las Vegas. The system would translate umbrella, rain. And then it was looking up what is the weather in Las Vegas, and it says, no, there is no prediction of precipitation in Las Vegas. And so if you have a confined domain, it actually works very well, and then you can sort of, at the edge of knowledge, it actually degrades gracefully. Whereas if you've got a purely rule-based system, for instance, then as soon as you get out of the scope of the rules, the answers have a tendency to get extremely entertaining.
Okay, excellent. So let me finish with what I hope is an entertaining, perhaps slightly flippant question. Okay. Will people be using the words or the terms big data analysis and IoT in 2020?
I hope not.
Okay, me too. Martin Kienzle from IBM Research, thank you very much.
Okay, thank you.
And thank you for watching IEEE CSOC TV. Thanks.